Yeah, thank you for your talk. So now it's time for question. So if you have a question, you can raise your hand or write down in the chat.
I think John's question was first.
Yeah, we have a question from John. John can.
Yeah, thank you. That's very interesting. I was wondering when you do this, isolate this gradient part that you introduced, there's, I guess, another part that would be related to some kind of curl, and I was wondering, is there a physical interpretation that you have of that?
Yes, so that's a very interesting question. So yes, the housekeeping part, there's an expression for it that shows it really measures kind of how non-conservative the forces are, how far away they're from the best, so to speak, the best grade approximation with the gradient. They define actually a set of steady state fluxes. Even for a steady system outside of steady state, they can be associated with a set of steady state fluxes. And I think they can actually be used to derive some kind of uncertainty relations or trade-off relations for the kind of cyclic part of the system. But this is not something that we have done yet or published yet. So I think we really focused on the excess part, but I think the housekeeping also is meaningful. Yeah.
Yeah. So Tom, yeah, you can ask.
Thanks,
question.
Yeah, thanks, Artemi. So this decomposition results from doing a variational minimization, right?
Mm-hmm.
So in general, do you end up with something horrible, or do you end up with something that's, relatively easy to interpret via that minimization?
Yeah, that's a good question. So in some cases we show that the minimization has a very natural and simple closed form solution, like for the oscillator, for example. And basically those cases are if you coarse grain the different reaction channels that mediate the same way, the same sort of stoichiometry, and you get something that looks like it could be detail balance, then you can use that to actually compute it in closed form. But in many cases, it's basically a numerical solution. So, I mean, and I would compare it kind of to the steady state potential, where often usually it's basically a numerical quantity, right? Like the steady state.
Okay, thank you.
Mm-hmm.
Oh, I have one short question. So, do you think the results can be extended to a continuous variable system with some kind of color noise, some true additive system in?
Yes.
Yeah.
Wait, so with colored noise, you said, or?
Yes, for example, kind of additive Brownian particle,
Mm-hmm.
something like that. So.
Yes. Yes. So great question. So for regular kind of well-behaved or Langevin systems, we can show that our decomposition reduces to a decomposition proposed many years ago by Christian Mays and Karl Nitochny. But actually, there is a very general way to write the decomposition as a variational problem of relative entropy. So I think any system in which the entropy production can be written as a relative entropy between forward and backward trajectories, this includes non-Markovian systems, for example, the decomposition can be carried out. And in that case, that's the form where it really looks like doing optimal transport, but the cost is kind of information theoretic cost. So the cost is basically distance to the reverse process trajectory distribution.
Okay, thank you.
Mm-hmm.
So it's time now. So thanks Atmi for a very nice talk.
Thank you so much.
Yeah. So the next the next speaker is Nicolas Barros. Nicolas, can you share the screen?
So hi everyone, can you hear me well?
Yeah.
Okay, so I'll share my screen. So if it's good for everyone, I'll start.
Yes.
So I'm Nicolas Barros, the first day. Hey, so nice.
Oh, perfect. Yes. So
Yeah.
yeah, please go ahead.
So I'm Nicolas Barros, a PhD student at the ENS de Lyon under the supervision of Ludovic Bellon. And I'd like to present you some work we did on probabilistic work extraction on an undamped oscillator. And so I thank the organizer for the opportunity of presenting these works. So as you think you all already know, when we are using stochastic thermodynamics, we describe mesoscopic system and the associated energetic distribution that we study, such as work and heat, become random distribution. So while in classical thermodynamics, if you do an operation in a system, such as a compression of the piston, you have to spend some work. So there is a work spent by the operator, which is always superior or equal to the free energy change in the system. And the fluctuation around this value of work are negligible. So there's no macroscopic violation of this expression of the second law. However, in stochastic thermodynamics, things are a bit different, and the work distribution is constrained by Jarzynski equality, from which we can deduce that the second law is valid on average. However, there is absolutely no problem with that on single trajectory level. The work that you have to spend is inferior to the free energy difference induced to the system because thermal fluctuations played in your favor. And in fact, this probability of observing such a transient violation of the second law, so having a work inferior to the free energy change in the system, is not bounded, except by one. And we are interested here in maximizing this probability. So we will do that experimentally using a cantilever, which is fluctuating in the air. So you see here like a tiny piece of metal. And we record deflection with high accuracy with an interferometer. So if we study its displacement, it behaves just as a particle, an underdamped particle, evolving in a well of potential. So I think my movie stopped, so I play it again. So you see it evolves randomly because it is sensible to thermal fluctuations. So it's evolving. So it has a movement in around a few kT. So it's sensible to thermal fluctuations, but we want to interact with it to do stochastic thermodynamics. In order to do so, we implement a feedback loop where at all time we will measure the position Z of the cantilever, we denote Z, which is proportional to the position of the cantilever. And according to its position relative to a threshold that we denote lambda, lambda will be the interesting parameter in the study. Depending on this position, we will apply a force that will shift its equilibrium position between two values. As a result, the dynamics is just of I'll play that again. We have just, the particle evolves between two wells separated by a threshold lambda and centered in minus or plus or minus Z0, which is the center of the two well, which will stay fixed throughout the study. Now, if we place the threshold lambda at an equal distance between the center of the two well, the potential is symmetric. However, there's no problem with choosing another value of lambda, creating an asymmetric potential, because in a way, the cantilever has more room on the left side, or here the bottom state, to evolve, implying that the energy of the potential is lower on the left side. We can thus create a potential that is tunable with two wells and measure accurately the position of the particle. So using the framework of stochastic energetics introduced by Sekimoto, we have everything needed to compute the interesting quantities, the interesting energetic quantities on the single trajectory level. So if we start from the expression of the potential, which is tuned by a parameter lambda, which tunes the asymmetry between the two wells, and using the data on the position that we record with great accuracy, we can compute the work along the trajectory or the heat. And if we change the system, so the potential in which the cantilever evolves between two states, the free energy difference induced by a change in lambda will be either computed using Jarzynski equality from the repetition of many experiments, or from equilibrium statistical physics using the computation of the partition function. Now let's have a look at the protocol that we will use throughout our study to try to obtain as many transient relation of the second law that we can get. So let us start with a double well of potential in its symmetric configuration. So there's a first threshold that we denote lambda I. And here you see that's the measured potential in light blue, which fits perfectly with the predicted shape of the potential that we introduced earlier in dotted black line. So if we start from this equilibrium configuration, here is what the initial probability density function of the potential of the particle, looks like. So we have half of the chance to be on the left side, of the chance to be on the right side. What we will do is, at one point, starting from an equilibrium state, switch the position of the threshold between the two wells from lambda y to lambda f, which will result in changing one of the two wells, rising the right well of the potential. Now let's see how it will work on the, how it will affect the work distribution. So you see, I'm at equilibrium and then I switch. So if I was initially on the left well during the switch, I can do the computation with the value of the work given by Sekimoto. I'll just notice that nothing has happened on the particle because the potential change happened on the right side. And the operator, which tunes the parameter lambda, has no work to spend. So roughly half of the time, the work spent by the operator is equal to 0. However, if the operator is unlucky, it will raise the energetic potential, the potential energy of the cantilever, if it was on the right side during the switch, from a given amount delta U. So if we have a look at the resulting work distribution, roughly half of the time, nothing will happen. Roughly half of the time, the operator will have to spend some quite large amount of work equal to delta U. And indeed, on average, the work spent by the operator will be larger, much larger than the free energy difference, as predicted by Jasinski equality. However, already 48% of the time, we could increase the free energy of the system because there's a free energy increase when switching from this configuration, which is symmetrical, to an asymmetric configuration. You can view it a bit as a compression of the phase space. So we have this free energy increase for no work spent in roughly half of the cases. You might notice that there are some intermediate cases. So if we have a zoom on it by switching to a log scale, you see that it fits the predicted theory. It just corresponds to intermediate values of when the particle is between the two thresholds. So things are a bit complicated for this very poorly sampled part of the potential. So the main message here is that if I'm on the left side when the switch happens, I have to spend no work and I observe the threshold variation of the second law. So to increase this probability, what we will do is just populate the left side, which is unaffected. And in order to do that, we will just start from an asymmetric potential. So that's the light blue configuration. And you see that the probability of being on the left side is higher than on the right side. So if we do the same protocol, so moving the value of the, so we set it out from an asymmetric double well, and we make it even more asymmetric. So 85% of the time, we are on the left side, which is unaffected. So 85% of the time, there's no work to spend. However, if you are really unlucky and the cantilever is on the right side, like so, when the switch happened, you still have to spend an amount of work equal to the potential energy increase that you have to confer to the cantilever. So if you're unlucky, we measure in 14% of the time, you have to spend some work delta U. However, in all cases, the free energy of the system still increases, even by by a lesser amount. And so if we repeat the experiments a large amount of time to properly sample all the probabilities that we can obtain during this experiment, we see that the mean work that we spend is still superior or equal to the free energy difference. But this time, more than 85% of the time, we happen to have a threshold violation of the second law. So you see, by just approaching the initial asymmetry closer and closer to the final asymmetry, we can go even higher because we can populate the left side almost as many times as we can. So this will increase the probability of observing a threshold variation of the second law. But if we do that, the change will be really small. And so the free energy increase will be ridiculously small. So that's kind of a trade-off. So we can observe 95%, we can observe a 95% chance of observing a threshold violation of the second law where the work spent is inferior to the free energy increase in the system. But if we do that, the mean work that we spend is always superior to the free energy difference, meaning that we always lose on average as predicted by the second law, and the gain delta F also decreases. So I thank you for your attention, and I'll be happy to answer your questions. And if you want to investigate a bit more on our work, you can find the article which was published last summer. So thank you very much.